Welcome back to Module 202C Part 2. In Part 1, we looked at the reasons why we have series RLC circuits and why phase shifting is important in certain applications. Now we're going to take a look at what happens inside the circuits, starting with our impedance triangles and what happens when we change our values of R, XL, and XC. We know that Z is dependent on how big both my reactive and my resistive components are going to be. The bigger either one of those components are going to be, it's going to change the value of my Z. Also, when we looked at series RL circuits, we saw that as we added resistance in series with the coil, those two resistances added together and also changed my Z value as well. So total impedance is dependent directly upon the value of R or X. What we see is that if we add R, we might have a smaller power factor, so we would have an improved power factor, but my total impedance for my circuit is increased. If I were to reduce R, then I'd see that my power factor is getting worse, but my total Z would be decreased. This, of course, affects both my total current on my circuit as well as my total power for the circuit as well. The other way that we can affect Z is by affecting our reactive component. So our X, being 10 in this case, if I were to change that value at all, I'd also see a corresponding change in my Z. If I were to take my X and divide it into half, what I would find is that my Z would also go down. Take a look at the power factor. My power factor also improved. And this time, with Z down, that means my current has gone up. Z is my total impedance. Therefore, less total impedance, more current goes through my system. So we can see how the Z and the R can both affect what my total impedance in my system is going to be. One thing we should understand by now is that my X total is going to be the difference between my XL and my XC. And if my XL component is larger than XC, I have a lagging circuit. However, if my XC is larger, then I have a leading circuit, and I need to make sure I represent that in my drawings. So you might be thinking, well, Stan, if canceling out the X gives me a better power factor, why don't I just line them up so my inductive component and my capacitive component are the same? Therefore, I don't have anything to do. I'll have a power factor of 1, which is what we want. Well, that's all great. However, that is what's called a resonant circuit, and they do exist. However, in a series resonant circuit, it does create a bit of a complication. If my XL and my XC are exactly equal, that means my Z value is going to be the same as my total resistance. So if my resistance is large enough, we don't have a problem. But if I have a very small resistance like we do in this circuit of 0.5 ohms, then I'm going to have a very large current. Using Ohm's law, we use 120 volts divided by 0.5. We have a current in this circuit of 240 amps. Now that's a lot. Now, we might be afraid of the ampacity, but that's not really where the issue is. What the issue is what is that ampacity doing to my inductor and to my capacitor? If we look a little closer and I solve for Z on that coil, I find that my total impedance of the coil is going to be 60.02 ohms. The total impedance of my capacitor is going to be 60 ohms. Using Ohm's law and my ampacity of 240 amps, I find that the voltage that will be across that coil is going to be 14,400.5 volts. And the voltage across my capacitor is going to be 14,400 volts. Now, who wants to touch that? The answer to that is nobody. Now, that's a very dangerous voltage which we want to avoid. This is a problem with the resonant circuit. If my resistance isn't high enough, I'll get a very high ampacity. That high ampacity will then create a very large counter EMF inside my coil, and it'll also allow for very large charge buildup inside my capacitor. So even though my supply is only 120 volts, each one of those devices will be generating their own charge that well exceeds what my supply is and could get up to dangerous ranges. So now that we know that resonant series circuits are not a good thing to have, let's look at more of a normal circuit that we're going to have. Here we have a resistor with a coil and a capacitor. Just like we did with our RL and our RC circuits, we can solve it the same way. We're going to start with our impedance triangle. Everything that's on the same plane, such as my resistances, all get added together. So my 6 ohm resistor gets added to the 5 ohms that I find inside my coil for resistance to give a total circuit resistance of 11 ohms. Now, since my XL and my XC are opposing each other, I need to subtract those two values. Here I have an XL of 20 ohms and an XC of 12 ohms. The resultant is that I have a total X value of 8 ohms. So my circuit total has 11 ohms resistance, 8 ohms reactance, which means my total impedance for my complete circuit is going to be 13.6 ohms for my total impedance. If you look at that and compare it with the total impedance of the coil by itself, you'll find that we're almost half what the total impedance of the circuit is. And that's because that capacitive component is offsetting the inductive component. When we look at our voltage values for the exact same circuit, using our values of our current, which is 8.824 amps, based on what our total Z was, we can find that my resistor is going to have a voltage of 52.94 volts. My coil should have a voltage of 181.94 volts. And then my capacitor is going to have 105.88 volts. If you were to add all these three numbers together, we'd be well over 300 volts. But my supply is 120 volts. The reason that works is that because my coil and my capacitor are going to have different values because they're at different phase angles. And my coil generates its own counter EMF, which means that its charge is going to be a little bit higher than what my source is going to be. When I look at my phase total, all my resistive voltages get added together to become a total of 97.06. My reactive voltages get subtracted from each other, so they're offsetting. So 176.47 minus 105.88 means I have a total reactive voltage of 70.59 lagging. And it's lagging because my inductive component was higher, which means that my total voltage is going to equal 120 volts at a power factor of 0.809. Once again, it's very important for us to understand that we need to take the phase angles into consideration because they're going to affect our total values. And it's very common to see some values inside our circuit to be much higher than what our source voltage is going to be because we are either creating more storage on our capacitor or we're generating more counter EMF inside our coils, depending what the current through them are. When it comes to analyzing the power portion of a series RLC circuit, you should find that all your triangles for your power will reflect the exact same triangles for your impedance, as well as the phase angle for all your voltage phasors. When we analyze the true power, we can take the resistance multiplied by the square of the current to find our resistive power to be 467.13 watts. Since that's on the same plane as the resistive portion of the coil, we can take the coil wattage of 389.27 and add them together. Our total power, our total true power for a circuit should be 856.4 watts, and that would be measurable with a wattmeter. For our reactive power, our Q component, we would take our inductive reactive power, subtract it from our capacitive reactive power. I would take my 1557.09, subtract it by 934.256 to get a total reactive power of 622.84. You have to remember that the power that's generated with the capacitor is feeding the reactive power that's required by the coil. This is why those two offset. One will feed the other, so that the total value that my system has to supply is much, much smaller. Since I have my VARs and I have my watts, I can use by trigonometry and Pythagoras theorem to calculate both my power factor and my total VA for my circuit. My total VA is 1058.82 VA with a total circuit power factor of 0.809. If you compare those two values with what's happening inside the coil, you'll find that my total VA is much smaller than the coil VA, and my total power factor is a lot better than my coil power factor. My coil power factor being 0.24, my total circuit power factor being 0.809. That means I've improved the efficiency of this circuit by adding a capacitor in line with this. Also, by adding that resistance, was also able to improve that power factor a little bit as well. This brings us to the end of part 2 of 202C. What I want you to understand from this part is how changing the resistance affects the total impedance, and how changing the capacitive reactance and the inductive reactance will also change the total impedance, and what that does to the circuit as a total. How does that affect our power factor? Why does building an XC value offset my XL value? What is happening with our power dynamics as far as my Q, my S, and my P are concerned as well? Go ahead and return to Blackboard, do the worksheet, as well as the knowledge check, and then you can continue on to 202C Part 3.